Good morning, everyone. In this video, we will be talking about concurrency. Okay, concurrency in terms of states are concerned in state diagrams. So we'll discuss about what is concurrency and what is aggregation concurrency, and then we will also see concurrency within an object and synchronization of these concurrent activities. The state model implicitly supports concurrency among the objects. Okay, so we have already seen so in any particular time so the objects can be in different states. Okay, of course the point is a class will have multiple objects, each of the object will be in different states, which we have already discussed. Okay, so that's how these objects are concurrently working among themselves. Okay, so in general the objects are autonomous entities that can act and change state independent of one another. That's what we have been discussing as of now. Okay, all the examples whatever we have seen basically fit into this one as of now. Okay, however, objects need not be completely independent. Okay, they may be subject to some sort of shared constraints that actually cause some correspondence among their state changes. We will see all the things in the coming examples. Okay, in the coming slides. So the first type of this concurrency we can easily see is with this aggregation concurrency. Okay, a state diagram of an assembly. Okay, so we have already seen what is an aggregation. Okay, so we have this sort of assembly class which has this sort of parts. Okay, a state diagram of an assembly is a collection of each part's state diagram. Okay, so we'll see that in an example. We again go with this sort of car example. Okay, the aggregation state in that one actually corresponds to the combined states of all these parts. So the aggregate state is one state from the first diagram, okay, and one state from the second diagram and one state from the third diagram, etc. Okay, let me immediately go to an example to make the things clear for you. Say for example, here is a car. So this is an assembly class. Okay, so this is this aggregation. Okay, relation between the classes we have already discussed about it. This car has this sort of ignition, transmission, accelerator and the brake. Okay, so these are the parts here. Okay, so all of them have one-to-one multiplicity. Okay, so these are these aggregations have one multiplicity here. Now the interesting thing is, at any particular time the car is in a state. Any state basically composes the substates in which each of these parts are there. Okay, that is the discussion about. So we will have one single state diagram for each and every of these parts, and then these four things. Say for example, here we have ignition, transmission, accelerator, and brake. Okay, so these four things together basically make this sort of state diagram for this car. And at any particular time, in which state the car is actually shows in which states each of the sub diagrams are parts of the sub diagram states are there. Okay, where it is. So let us discuss about this sort of each and every of the state diagrams of each and every part. Okay. So, okay, let's proceed one after the other. So ignition, okay, so it will be in originally off state. When you turn key to start, okay. So the interesting cases we will discuss later. Okay, so when we turn the key to start, we will be in the starting state. Okay, what is this guard condition? Transmission is in neutral. We'll discuss that one. Okay, later. But the thing is, originally you are in off state. Okay, when you turn the key to start, it will basically turn to this sort of starting state. When you release the key, it will go into this on state. Okay, so basically you press the button and then you released it. Okay, then the engine is basically in the ignition state. Okay, of course, if you turn off the key, then it will go into this sort of off state. So this is the state diagram for this ignition part of this car. Okay. Similarly, we have the transmission. This transmission state diagram, we have discussed in one of the earlier videos in detail. Okay. So you basically start. It will be originally in the neutral state. If you push this sort of reverse, it will be basically going into the reverse state. If you push N, then it will basically be come into this sort of neutral state. But in neutral state, if you push F for forward, okay, it will basically come into this forward composite state. At that time we have particularly we discussed like, okay, so that means like it will actually start at this one. So when you push there, it will come to the first state. Okay. We also have discussed like then upshift will basically take it to the second and third. Okay. Similarly, downshift will basically get them down. Okay. We also have seen like from the composite state you can have a stop. Okay. So which always will basically lead from any of the states. If a stop will be there, you will come to the first. So this thing like this transmission we have discussed in one of the earlier videos in detail. This is all about the additional features. So from the forward state, if you press the N, it will basically go to the neutral. And this is the state diagram for transmission. Now for the accelerator is concerned, like you will start again, and then like originally you will be in this sort of off state. Okay. When you depress the accelerator, okay, you are pressing this depress the accelerator, then you are basically turning to the accelerator on state. And then like when you release the accelerator, you are basically coming to the off state. The same thing happens with the brake as well. Okay, when you depress the brake, then you are in this sort of brake on state. Originally you are in the off state. And when you release it, you will be releasing the brake. That means like you will come back to the off state. Now interesting thing is what this aggregation thing is stating is like the state diagram of car is actually a combination of all these three. At any particular time in which the state of the car is basically shows like in which state the parts are. Say for example, at a particular time, like the state of the car can be, it is in the engine is on, ignition is on, and then like say for example, it is in the second gear. Okay, okay, that means like and you are pressing the accelerator. Okay, so on, and the brake is in off state. That could be one single state of a car. Okay, now hope the things are clear for you. Part states actually interact in more interesting cases. Okay, so the example we are considering here is also an interesting case. That's what like I will be discussing. Transition from one object can actually depend on another object being in a given state. Okay, that's where like these sort of interactions also make it interact. I mean, very interesting. Part states can actually interact. So now let us come to this one, this guard condition. Okay, so when you are in the ignition off state, when you turn the key to start, okay, but the transmission should be in neutral state. The transmission should be in neutral state. Then only like it will be going to the starting state. Okay, assume like the ignition is off and then like you are in some second state or something. I mean like if you are stopping it, then you are basically coming to the first state. Okay, so in the forward state, then like you cannot basically start it. I mean like you cannot start the ignition. Okay, so in this particular state diagram. So the basic condition is like you are actually trying to see like the transmission. Okay, so which is these parts. Okay, so the transmission's substate, okay, state should be in neutral state. That means like only when you are in this particular state, then this off can basically go into this sort of starting for this ignition. This is an interesting case here. Okay, that's about this sort of aggregation concurrency. Okay, hope that is clear. Now let's move on. So there can also be a concurrency within an object. Okay, what we can do is like we can partition one object into subset of attributes and links. Okay, so that is a single class. Okay, so we have actually made it into subsets of attributes and links, each of which will have its own subdiagram. Say for example, like there is a class like I made it into two parts. Okay, partition that one into two subsets. Okay, and each of these subsets will have their own subdiagram. I will show you the example in the coming slide. Then basically like the state of an object basically comprises one state from each of these subdiagrams. Okay, earlier like when we have seen the aggregation concurrency, it is like composition of one state from each of the parts state. Whereas when we are actually taking a single class object, okay, object from a single class, and when we are partitioning that thing into subsets of attributes and links, and each of them have its own subdiagram, then basically like the state of an object is basically one state from each of the subdiagrams. Okay, the subdiagrams also may not be independent. Okay, so the same event can basically cause the transitions in more than one subdiagram. Okay, the UML notation for this partition is basically like composite state into regions with dotted lines. Okay, so I will show you the example now. So basically just don't care about the example. Okay, so I'll explain the example. Here is the composite state. Okay, And here is the partition, which actually says like this is the state diagram for that sub part, okay, within this particular state, okay, and this is for the second sub part, okay. So we partition it like this with the UML. Now let us come to the example. This is about a bridge game being played. So it's a card game, okay. To be frank, like I also don't know this game, okay. So for that only, like I'm leaving a reference of a YouTube link. If anybody is curious, like you can basically play, yeah, learn and know like how the game is actually played. To give you a quick summary, like there are two different teams are there which are playing. So basically, like they sit in opposite sides. Okay, so they are in pairs. Okay, so four of them are playing. So basically, like these north-south guys are in one team, and then like east-west guys are in another team. Okay. The basic idea is like they will be playing this bridge game somehow or other. Okay. So the initially both of them are not in vulnerable state. So the point is like the game goes something like this. They will play the game using that certain rules. Okay. You check the video. Okay. Card games are out of my reach usually. So basically the point is like once you basically win a game, okay, you will go to a vulnerable state. Okay, so basically like what will happen is like, okay, and then like you have to play, you have to win two games in sequence so that like you actually win the actual game, which is called like you won the rubber. Okay, so it's terminology, games terminology. So initially both these players, okay, so this north south, okay, and then like east south, both of them are in this sort of starting state and not vulnerable state, both of them are. Now, say for example, this north-south team basically wins the game, then they basically go into vulnerable state. Okay, so that means like their cards are open or something. Okay, so you basically go and check, and then like the basically like the opposite guys, these east and west guys. Okay, they are trying to win this round. Okay, if they win this round, then they also will go to the vulnerable state. The other one will basically move back to this sort of non-vulnerable state, and then like it basically has to go like this. Okay, and eventually like if you win both these games, okay, say for example if north south team basically wins both the games, then they basically win the rubber. The same thing will like east west wins the both the games, then they will also win the rubber. There is also like total counts of the points and everything, like you basically go and check it. As far as the state diagram is concerned, I am all interested in is like when you are in this sort of playing rubber state, okay, that's a composite state. And then like say for example, now you can actually represent like partition this sort of class into like this north south being vulnerable and east west being vulnerable. Then you can have like say for example a state diagram for each of these subparts. One state diagram for this north south vulnerability, another state diagram for this east south vulnerability. Okay, and that's how like once whoever wins like is winning the game. So this is about this sort of this concurrent states, okay, within this one. So this you have partitioned that one, so at any particular time like you have this the state is, okay, so for the complete playing rubber game is, say for example the north south is in vulnerable state and the east west is in not vulnerable state. So at particular time like the state is like this one, so he has transition, this sub diagram has transition to here, but this has stayed here, okay, after the start it is in this particular state. Okay, alternatively it can be in the reverse state as well. Okay, so north south is in not vulnerable state and east west is in the vulnerable state. Okay, so that's about this sort of the concurrent states, okay, when within an object. Now let us move to the third one, okay, synchronization of these concurrent activities. Okay, so this is third type of this sort of concurrency in this discussion. Sometimes one object must perform two or more activities concurrently. Okay, the objects may not synchronize the internal steps. Say for example, like think about like a cash dispensing machine dispenses cash and also like it has to return the card to finish this sort of transaction. Okay, so that means like that particular object in that particular case it is doing this sort of two activities concurrently. The object does not synchronize the internal steps of the activities but must complete both the activities before it can actually progress to its next state. So when this sort of machine, ATM machine, for example, when it is dispensing this money and also like it is trying to return the card, it does not matter like in which order like the user is actually taking, whether you take the cash first or like whether you take the card first. How it depends up to the user. Okay, the order in which they are taken is completely irrelevant in this case. But the point is both the tasks should be finished so that the transaction is actually complete. And that is where, like, say, for example, you are actually splitting the control into concurrent activities. One is like dispatching the cash, another one is like, say, for example, returning the cards. And eventually you have to merge the control again. Okay, so once you basically split the, for concurrency, like this object basically splits into these sort of two different activities. Okay, splitting control. It basically have to merge it again. Okay, so that like it basically comes back with this sort of next activities. Now I will show you the example that will actually make it clear for you. So here is the cash dispenser. So originally it is setting up. When it is in the ready state, okay, this is called basically a fork. Okay, so the fork is like basically the control is actually forking. Okay, a transition that forks indicates splitting of the control into concurrent parts. So this is again like a composite state. In this, like the parts are like this. Say for example, this state where the activity it is performing is like we have already seen this one. It is performing a do activity, and it is actually dispensing a cash. If the cash is actually dispensed, this basically like this transition is complete. Okay, I mean like the state is complete, and then like you are fine, and then like it is finishing. Similarly, okay, so with the fork, like you have another thing which is parallel being done. Okay, so this state actually you are doing the ejecting the card. Okay, that's also a do activity. Once this state is finished, like you will basically finish into this. Okay, so when the transition files like two concurrent substates become active. So both these substates are becoming active. So that means like this state and this state. These are two substates for this total state. Okay, total composite state. Okay, component become active and execute independently. So that's how like you are achieving the concurrency here. And this is the basic advantage of this sort of forking. Okay. I'll come back to the example for discussing the further things. Like once this cache and these things are finished, like you will basically go to this sort of ready to reset state. Okay, that is clear. So any transition into a state with concurrent subdiagram activates each of the subdiagrams. Okay, so basically what this statement basically shows is, okay, any transition into any of the substates will actually start all the other subdiagrams. Okay, so basically into a concurrent subdiagrams activates each of the subdiagrams. However, like UML actually mandates using this fork, or else like fork in the diagram is actually not necessary. But UML, to make it simpler, make it clear, like it mandates using this particular fork. Okay, the fork also like from the UML side, like it also needs this sort of merging. Okay, UML also shows explicit merging of concurrent control by a transition. Okay, if you are curious about this merging is concerned, like I can show you in our star UML. Okay, so the way like we have this sort of merging is there, which is fork is there, and we have this sort of merging with this sort of join. Okay, so the same thing in the join, like in the fork, like the way like they are coming, okay, going out, so you will have a merge here. Okay, so which is called join. So you will basically have this sort of lines coming. The UML would actually need it. Okay, UML also shows explicit merging of concurrent control by a transition. But the interesting thing is, like if you look at this diagram again, so we already have discussed this transition don't have any label. So there is no event here. That is basically a completion transition. This we have discussed in our earlier videos clear. Once this activity is completed, this other transition immediately fires. So that is about the completion transition, completion state. So basically like unlabeled, so the completion transition from the outer component state to another state actually indicates implicit merging of the control of this sort of concurrent control. So in this one, like say for example, if we are tracing the transition to the this sort of ready to reset state, that means like both of these things have actually completed. Both these things have actually completed. Okay. So the composite state completes when each of its concurrent substates is complete. Okay, so that means like when you are going for the merging, and then like if you have that line, So the composite state is completed. It's like both the substates have actually completed. Okay. So in that case, like it is also interesting to note like a transition from a single concurrent state to a state outside the composite state actually causes the other concurrent substate to terminate. See the point. So any transition into a state with this sort of concurrent diagram actually activates each and every subdiagram. Similarly, like any state which is actually going out with any event, any transition that is happening, will terminate everything. Okay, so that's why like this sort of fork and merging UML mandates it. So the point is like if you don't have the fork and then like if a transition is going into this line, so basically what it means is like by default both of these things will start. Similarly, like if it is closed and then like it is basically leading it to this sort of ready state. So for example, even if the second substate is in this state, that will also terminate. Okay, it will terminate the process in the middle. That's why like having this sort of exact forking and merging is actually important with this sort of UML. Okay, so that's about this sort of synchronization of control. Okay, so how you draw this diagram actually affects a lot. So if you have a single merge here, okay, the way like even here in this sort of completion state it is showing the state. If it is a single merge here, okay, then both the things will complete and then like you will basically go to the next state. However, if you don't put a merge and then like you draw a line from here to here and here to there, okay, so if you put two lines, two transitions, the point is like the moment one of the transition finishes, okay, since you are coming out of this sort of composite state, the other substate, sub diagram, wherever in whichever state it is, it will basically terminate. Okay, hope that is clear now. So that's about this sort of concurrency. Okay, so regarding the reference are concerned, we are still in the chapter 6 of this object-oriented modeling and design with UML, second edition, Michael Blaha and James Bob. Okay. Okay, for the people who are interested in playing bridge, like you can check this video, okay, YouTube video, and then learn more about it. Okay. Thank you very much for your attention.